Okay, this is the second part of Chapter 8. We're going to talk about arc length and how that relates to radian measure. Okay, the length S of the arc on a circle of a radius r by the central angle of theta, that's what that Greek letter is, in radians is given by the product of the radius and the radian measure of the angle. So it's pretty simple to get the arc length. You multiply the radius times whatever the angle is in radians. Okay, so this is the theta. And so the arc length is just whatever the radius is times the measure of whatever angle we're going around the circle with in radians. Okay, so example, find the arc length of this has a radius of 18.2. Find the length of an arc intercepted with essential angle of 3 pi over 8 radians. Okay, so we just multiply those two together. Okay, so no big deal. So you can leave it in terms of pi like this, or you can do the decimal approximation like that. Either way is good with me right now. So sometimes the book has the answers with pi. If they say use the exact answer, you have to have the pi there. If they say give the approximate answer, then you can just multiply everything out. Angular speed. Okay, we use the Greek letter omega for that. Looks kind of like a weird W. It measures the speed of rotation and is defined by how many radians we go through divided by time. Okay, time can be usually in seconds, but it can be any number of times, usually seconds. And then the linear speed, v, is defined by the arc length, how far we go around the arc, in divided by time. So the distance we travel, just like any other speed, distance we travel divided by time, where s here is the arc length. Okay? So since the distance is the arc length s, and we had, that on a slide before we said s was r times theta, we're going to replace that s in this equation with r times theta. So, and since theta over t equals the angular speed, we can also rewrite it like this. We can also write the linear speed equals the radius times the angular speed, right? This theta over t is the same as the omega. So we can see it a couple different ways here. So the arc length divided by the time, which is the radians times theta over t. Theta over t is the angular speed number. Okay, so a couple different concepts here you may not have had before, but they're pretty simple, but you may have to look these up or watch the video again. Okay, so a typical problem like this is something traveling around in a circle, and they give us a problem here, the satellite traveling around in orbit that's 1,600 kilometers above the surface. It takes 2 hours to make an orbit. Now we're going to assume that the radius of the Earth is about 6,400 kilometers. Find the linear speed of the satellite. Okay, so they gave us this, the 64, and then a nice little picture here. It's not to scale, but it's a nice picture. Get the idea. So the distance for our radius here is going to be 1,600 plus 6,400 is 8,000 kilometers. So for one orbit, theta equals 2 pi. So the s equals the radius, 8,000 times 2 pi. And t, we have 2 hours. Okay, so our theta is 2 pi, our t is 2 hours, our s is 8,000 times 2 pi. So we're trying to figure out the speed here, the linear speed, is how far it went. So the s is this number, 8,002 pi divided by 2, which, the 2's canceled out here, and we get 8,000 pi, or about 2,500 kilometers per hour, which is pretty fast. Okay, so how far did it travel? This was the other one. So we do the speed times the time. So this is how fast it was traveling, 8,000 pi, right? And for how long did it travel? It traveled for 4.5 hours. So our time was 2, so our time was 4.5, so we just multiply 4.5. And in 4.5 hours, it traveled approximately 110,000 kilometers. Okay, so just quick introduction to angular speed and linear speed. Okay, so that's all that's in this video. So we're just going to do those two concepts, and I'll see you guys in class tomorrow.